All right. We will be going over this exam. It's from winter 2024. And we're gonna start from Turing machines and then go over a bit of pumping lemma. And then towards the end, we'll circle back to the uh, older materials such as context-free grammars and regular expressions and automatons. So we're gonna start with problem number 4. I'm just gonna copy and paste it to the sketchpad so I could actually write on it. Oh, right. This is our Turing machine or our Turing machine instructions. The way to read these instructions is that the first part, the Q, or whatever is on the leftmost, is the state that you're in. And then the second part is what character you see on the tape. I'm just gonna say char, you see. The third part is the state that you go to. The fourth segment is the character, what character you change the character to. So over here that you see a lowercase a in state Q, and then you could change that to uppercase A. Change character, or you could also keep it the same. Change char, and the uh, fifth is the direction you turn. So over here, you're turning right. You could also turn left. Um, I'll make this more smaller. So you could either turn right or you could turn left, right? Okay. Now that we got that out of the way, this is our machine. These are all of these states. Uppercase Q is all of these states. And over here is given that we have states Q, X, Y, W, and T. And then sigma is our alphabet that we could input, right? So similar to like regular expressions or such, we're given any alphabet that we could put on our and feed it to our Turing machine. That's in our language. And then gamma, this is gamma. These are the tape alphabets. So Turing machine, we use this tape. And then our tape alphabet is gonna be our sigma is a subset of our tape alphabet. That means that anything on sigma could appear on the tape, but we could also have additional tape alphabets such as uppercase A, uppercase E, and uppercase K, and also blanks. So the tape is filled infinitely with blanks in the beginning, right? And it goes all the way to the right side, infinitely to the right, and it's all just blanks. To the left side of our tape, we could fit in our inputs, right? We could fit in like A, B, C, and then once we fit it in, we could also change it, right, on our tape. And then this we could either turn this direction, we could either turn the directions right or left, okay? And yeah, and we could also change states. Um, there's this tape method, and there's also method to do with the automaton. It really depends on preference, but I would say it to work with what works best for you. I'm gonna show both the method and then go on about that. Okay, so that's gamma. And then we also have our F. If the question gives an F, that means that F is the final state. If you get to a F, then we would accept that regex or that input, right? But if there's no F given, if it's just this, if it's just Q, sigma, and then gamma, then that means that our machine either halts, that means that we stop, or it diverges. Diverges means that, okay, so remember how I said that our tape has infinite amount of blanks? Diverging basically means that you see a blank and then you just keep on turning right and then replace the blank with another blank and don't change state. So some example of that would be over here, right? You're in state X, you see a blank and then you replace it with another blank and then you don't change state and then you turn right. In that case, it's basically saying, okay, I'm in X right now and I wanna keep it 2x, but I wanna change my direction to right side, and then I'm gonna see another blank. And then I'm just gonna continue on going. And this makes a problem because the tape is infinitely filled with blanks, so the machine would never stop. Right. Now let's get on to the problem. Oh, okay. So M has a one-way infinite tape to the right side only. B is designated blank symbols. M accepts by final state. Okay. So let LA be the set of string which M accepts, right? So LA is all of the strings which M accepts, and we want to come up with a regular expression that defines LA. If such regular expression doesn't exist, state that it does not exist and prove it. So, uh, what is saying that we want to come up with all the strings in this machine that reaches the final states, right? The final is the accepting state, and over here, our final state would be T. I kind of crossed it out, but uh, right, it's T. So we wanna reach T. Let me get rid of this. Okay. Okay. First, I'm gonna do it with the T method. And then we could do the automaton. Actually, I think the automaton would be a better method to go over first because I think more people are familiar with the finite state machines. It's similar to that, where we have a lot of states and then we change states when we see a letter or so. So let me make this smaller. Okay. So we're gonna start with over here it says our starting state is going to be Q. Okay, so these are our states. This is our sigma, our tape alphabet, and the instructions, which is basically this, right? Our transition set. And then this is our starting state, lowercase q, and our final state, uppercase F. So okay. So we're gonna start with Q. And then From Q, we could see an A, B, or C. A, B, C, and then this all will take us to state X. So from Q, we could reach state X via A, B, and a C. And we see that we turn those into A into uppercase A, B into uppercase E, and C into uppercase K. Okay, so that's what we're gonna do. B into uppercase E, and then C into a K, and we're turning right. And then once we reach state X, we're going to take a look at over here. This is the state we're in, right? This is the state we're in. We could see A. If we see an A, that means that we replace it with the A, but then we reach back X. So it's basically like a loop, right? You're in state X, you see an A, you could go back to state X. That's a loop. And we're turning, sorry, lowercase a, and we're turning right. Okay. And then if we see a B, we change state to Y. Okay, we don't do anything to the B, we just turn right. And if we see a C, that's also a loop. We reach back to state X, but we're turning left, okay? So over here, we could also see a C, and we're turning left. And if we see a blank, that's also a loop. We're turning right. But in the case that of LA, we wouldn't want to eat a B or see a B in state X, right? Because that means that it would diverge. This is L diverges, and we're trying to find a regex for LA for part A. So LA, we're trying to come up with that regex, and then in state Y, we could see a C, and once we see a C, we go to state W. From the left side and state W to go to state W to state T, which is our final state, we have to see a A from the right side. Okay. All right. So this is our path. We start from Q and then we have to get to T, right? T is our accepting state. So that's the path that we have to build. So from Q, we could take either A, B, and C. That would all get us to X. A or B or C. But we have to remember that this all changes to uppercase A, E, and then K. Let me make this smaller. And then after that, from X, we want to go to Y. But in state X, we could see, we could loop on a A, right? We could loop on a A. Let's put that as A star. And then if we see a C, we could also loop on a C. So that's a C star. we're turning left, or C. And then at the end, we have to see a B. So this could also be zero, right? So from over here, we don't really have to see any of those. We just have to see a B to go to Y. And B doesn't have a star on it because it can't loop. It changes state, right? That we cannot go back to state X if we see a B. We change states. And then from Y, we want to go to W by seeing a C from the left side. So this is, so okay, we were in state X when we saw that B, right? And then we changed state to Y. In Y, we want to see a C. So we're looking to the left side, right? C from the left side of B. Let me move this. On the left side of B, we want to see a C to go to W. And then from W, we want to see, so we want to see an A. After we see a C over here, we still want to see an A, um, like this. But there's a problem with this because whenever we see a C in X, right? Whenever we see a C in X, we have to go left. And if I keep on trying to go left on C, that means that A would have to come before C, like after C, because A is turning right and C is turning left. So, like for example, let's say I have the input A, A, C, B, and I'm using this machine to travel to get to T, right? So I'm in state Q right now, and then I see an A. I see an A. I'm like, okay, I turn this into uppercase A, and then I go to state X. I'm in state X. I see a lowercase a. I turn right, right? Okay. I turned right. I'm still in state X, and then I see a C. When I see a C, I have to go left, and then I'm like, okay, I see an A. I turn right, and I see a C. It kind of gets stuck in a loop, right? Because okay, I'm turning left and then I'm turning right. I'm turning right and then I'm turning left. Um, that doesn't get us to T. It just gets us stuck in state X, right? So let's try another input. Let's say A, it doesn't really matter whatever I pick for Q, right? Because everything from Q, A, B, C gets me to X. So let's say I pick B. And then in state X, I'm like, okay, since I get stuck in A and I need a C to progress to W, I'm going to get rid of this A, right? I'm going to just see a C and then a B. Okay, I'm in state Q, I see a B, I turn this into uppercase E, and then I turn right to state X. I'm like, okay, I'm in state X, and then I see a C, okay? I see a C in state X, and I have to turn left. Left means going this way, and this way I see a uppercase E, right? So, um, there's no instructions. So when I see a E in uppercase E in state X, there's no instructions for that. So the machine would just halt. And it still does it, or like halt and then reject because there's no accept, it doesn't reach the accepting state. There's no way to get from Q to T, and that's why I think that the answer to the regex is that it doesn't exist. Um, So since it never exists, accepts, then it's going to be the empty set. None of the string accepts, right? Okay. Any questions?
I had a question. How did we know that we would start in state Q?
It's going to specify in the question. So if you take a look at the M is the set of states, right? And the set of sigma that our alphabet that we could input on the tape, and this is the tape alphabet. This is our transition set, and this is the state that is going to start at Q. So this is where Q is, and this is where we're going to start.
Okay, thank you.
No problem. And then F is our final state. On some question, it specifies F, some questions it doesn't. When it doesn't specify F, that means our machine either halts or it diverges. In this case, since there is a final state, the machine is either accepts, rejects, or diverges. Any other questions for LA?
Yeah, I have a question.
Yeah.
On the transition step, like on the state Y, read
Mm-hmm.
C, next statement W, write C and move left. How does it work?
So you're asking me in state Y, right? If you see a C and then you go to state W and then you move left, right?
Yeah,
So
because I understand in the state X, read B and
mhm.
move to the Y, right? And move to the right and read C and move left
Yeah.
and move left and then the left move left. So the head gonna the move to the alpha beta before C, right? I mean
Hmm.
left side and left side alpha beta should be
So,
the B, not A, right? So
yeah.
if we want to go to the final state T, we must read A, but there's only B on the left side of C.
Yeah, exactly.
I'm right?
Yeah, yeah, you're right.
Oh,
Because you
oh,
have to see a B to go to Y.
Y, C. Okay, I got it. Thank you.
Hmm. Anybody else have any questions for LA?
Oh, one more question. I'm so far I'm confused with state X, read C next to X and write C and move to the left. I don't know. It doesn't make sense. I mean, if we just use the C star to represent it, because it doesn't move to the right. I mean, if this transition is moved to the right, I mean, if we write okay, C star, I mean, it makes sense, right? It's not
Hmm.
good, but it doesn't move to the right. It moves to the left.
Yeah, yeah. So it's basically saying like, okay, let's say I have a bunch of CCCs, right? That are represented by C star, right? Okay. So I'm in state X right now, and then I'm seeing a C. So I'm just gonna keep on moving left and then left, and I'm still gonna be in state X. The thing about this is that none of the strings is going to get to the accepting state, right?
I
Which is
mean,
T.
I mean,
That's why.
I
Hmm?
mean, since by this transition doesn't don't work anything because in the queue, right? We read A or B or C and write as the AEK, right? And
Yeah.
next, okay, see, after the oh okay in the state X we read A and write A and a loop, right? So
Mm-hmm.
in so far we only have a capital A, capital E, capital K, right?
Yeah.
Uh, and small a, right? And one
Mm-hmm.
C and one C. But when we read C, when we read C and move
Yeah.
to the left, I mean there's no C to read because there's only capital A, capital E, capital K, and A.
You're thinking about state Q, right? In state X, you're allowed to loop on infinitely on A's and C's and blanks. I mean, blanks would be diverging, so let's get that out of the way. So it's just basically saying that I understand what you're saying. So, but think about it this way. I assumed like you're saying like, okay, I see a A, right? And I move to the right. And then I see a C. And then I just go back to left. So that's like, it's you're stuck basically in a loop in state X where you're just turning right and then turning left and then turning right. Um, so yeah, you're right in the sense that you could only, but like I'm saying it technically, you could see multiple C's, is that you just never read them.
Okay, so the machine will start in this step, right? The Z L X Z X C X C L. The machine will start here, right?
Yeah, yeah, it gets
Okay.
stuck.
So it gets stuck. That means
It
just
rejects.
and it means what? Rejects, right?
Yeah, exactly.
Or the hold, right?
Mm-hmm.
Oh, that is hold. Oh, okay.
Yeah,
Okay.
yeah,
Okay.
yeah. That's how.
Thank you.
Um, so, like I said, if there's a final state, then they're not gonna call that a halting state. They're just gonna call it a reject. But reject is basically what if you don't reach the final state and you're stuck somewhere else in the machine, but you're not stuck on the diverging. You're not like seeing a blank and going uh to the right, right? You're just stuck somewhere in the machine. Okay. So let's do L reject. And that's going to be the set of strings where the M rejects the input, right? So let's see in Q. In Q, where it could reject is that if it doesn't have any instructions for what to do if it's Caesar, right? So I have A, B, C. All of them get to X. Well, what if I see a blank? If I see a blank on the machine, that basically means that I give the machine nothing or I feed the empty string. The empty string, aka known as lambda, right? If I feed it lambda, then the machine wouldn't know what to do with it because it doesn't have any instructions to do it. Like, do I transition to another state? Do I keep it the same state? Do I, diverge on this? So one of them where rejects would be lambda, or we could build a path, right? We could go to from Q, we could go to X, and then from X we get stuck over here. So let's say from Q we get to X by taking A, B, C, A or B or C. And then after that, we get to state X, right? And state X, let's say I want to get from X to Y. So I can see A, but I want to avoid seeing a C because I would get stuck in that loop, right? So I'll see an A, and then I could see any A or I could see zero A, but I would have to see a B, right, to get from X to Y. Let me write this a little smaller. Uh, and then from Y, uh, in Y, I could see anything else, but then the thing is, okay, I get to X, and then in X, I could see any amount of A's, and then I move to Y, and in Y, I only have an instruction for C. What if I don't see a C? I could, even if I do see a C, it wouldn't make sense to go left on it, right? Because left would be this side. So I could see anything after that, A or B or C, and it would still never reach the final state. And I'm not allowed to diverge on Y. Okay, that's another way. Or the other way is just getting stuck with this C over here. Um, or I could see a or B or C from Q, and then in X I could see a C, and then I turn left. I could see I'm gonna see a uppercase A, uh E or K, and I don't have any instructions to process this, right? Nothing to process it, so my machine would stop. Like what I mean by that is that okay, it doesn't have any now I'm in state X, right? And I turn left in state X and then I see uppercase A. I have no instructions for that over here. And then anything else could come after it, or nothing could come after it, but this regex would still be rejected, right? Because my machine would halt. Any questions?
I have a question.
Yeah.
For the lambda part, because this machine start from the Q.
hmm
So I mean, why we don't write the A or B or C
For the lambda?
for the lambda? Why it seems like you just skip the Q and directly go to the X?
No, so this lambda I wrote because I start from Q, right? In Q, I have no instructions for lambda. So in Q, my machine wouldn't know what to do at this. Lambda basically means a blank, right? It doesn't mean it means that there's no input given. So Q, I see a blank. My machine have no instruction to process this, right? Does it go to
Oh,
another state? Does it stay? Does it diverge? No, no instruction. So it pauses.
okay. Another question is for the third part of your question is A or B or C. If can I just add a A star between the A or B or C and C? Can I?
You
See,
want to add a star over here?
no, just no, the before before C.
Over here.
Yeah, can I add here? But seems like it also the reasonable because
You cannot add a star over here because this is in state Q, right? In state Q, you can't loop. You have to change
I
state
mean
to X
no, not A star. I mean add a A star before the C after the
before the C
yeah in the middle. Yeah.
over here.
If I answer like this, am I right or this is wrong?
Uh, I would say not to put a star just because you saw like it gets stuck over here, right? And it just like it's a repeated loop. Um, I would say this is more of diverging just because the machine never stops going back and forth. So you turn right on A and then turn left on C and then turn right on A, turn left on C. Um, so I would say that that's more of a diverging string, not really stopping string, you know? So I wouldn't say to add a.
Oh, that is a diverging, right?
Mm-hmm.
Mm. The reject hold.
So for L sub R, we're just finding every single set where the function will just halt.
Yeah, so that includes any transition that's not given for any inputs, such as, you know, in Y, there's no transitions for A or B. Uh, but then again, this would just halt over here because if you see a C, you'd have to turn left, right? If and you turn left and then you see a uppercase A, E, or K, the machine has no instructions to process those in state X.
Okay, my question is, in which situation I can use my answer? I mean, that answer has a
You
star.
could you could use it in L diverging.
Oh, diverging. That is a reject. Reject.
Hmm.
Oh, reject only means hold,
Yeah.
right? Only hold.
Hmm. Yeah, exactly.
So I mean, I can understand the reject equal to hold.
Yeah. Yeah.
They
Reject
are
is the same thing as halt.
they are equivalent, right?
Yeah. Hmm.
Oh, okay. All right. Oh, thank you so much.
Hmm. So like Steven said, the other one would be where you see A or B or C, and then you could have A star, right? And then a C, and then you could have anything else after it, but this would be what do you call it? This would be diverging because it goes back and forth and it doesn't halt. Let me just copy this. Yeah. Or you could just have A star, right? A star, it would just keep on going right. But then it could also stop at a blank and then it would diverge at state X. Um, let's copy this. Okay. Any questions for L diverging? Okay.
Oh, okay. Well, I have a question. How about the blank looping?
That is taken care of by this one. So over here, you could have a, okay, let's say you have A, B, C, right? To get from Q to X. And then in X, right? You could loop on A, right? You could loop on A, but if A is not there, you see a blank, right? Or you could have a infinite amount, but eventually it has to stop at a certain A. Let's say I have three A's or five A's, and then after that, we're gonna have to see a blank in state X. And when we see a blank, we turn right, we see another blank, we keep on going right.
Oh, okay. So the last one will cover these two situation, right? It's the looping the blank looping and the A looping, right?
Yeah.
Oh,
A and C looping would look something like this, right? A goes right, and then C goes left, and then A goes right, C goes left. Oh yeah, if this is empty, right? This could be empty, so we have to put A there. Because to make sure there's at least one A.
oh, okay, I see.
All right. And then I'm not really putting a C star over here because you could get a C star from here, right? You could have like C, C, C. But again, it never really reaches it because once it sees a A and then it sees a C, it goes to the left and then it goes right again. Oh, um, right here. Any questions? Okay. If not, we're gonna do a pumping llama question. So any other question on Turing machine? Let me see the comments. Okay. Okay. We're gonna do pumping llama. Also, this recording will be posted sometimes maybe over the weekend or so, but it's getting recorded right now, so you could feel free to check back on any Turing machine questions. Let's do pumping lemma. The exams that I'm referencing right now has a pumping lemma for regular expression, I mean for regular language and also for context-free grammar. We're gonna do the regular first. So that's question number 5. Okay. So we have our sigma given A, B, C, G, and our L is defined by those strings over sigma that satisfies all of these properties. Okay, symbols in the string occurs in alphabetical order. So, A, B, C, G. So, and the letters of A's is less than the letters of B's. Okay, the numbers of C's is divisible by 4. The number of G's is divisible by 3. Write a complete formal definition of a context-free grammar that generates L. Okay, so these are our constraints. We have 4 constraints, 1, 2, 3, 4. Number 1 seems pretty easy, right? So it's just alphabetical order. And uh, this also is pretty easy, I'll say. So the numbers of A's is less than the number of B's. That just means that if A is, let's call it N, and B is M. N has to be less than M. And the number of C's is divisible by 4. So A to the N, B to the M, and then C is uh C would be something divisible by 4. So let's call it 4W. And then G is divisible by 3. G to the 3L. Write a complete formal definition of a context-free grammar that generates L. If such grammar doesn't exist, state that it doesn't exist and prove your claim. So this is context-free because, okay, the way that context-free is violated is if we have 2 of these things. We have a link that intersect each other, or we have 3 plus relation. So what is meant by that is that let's say A to the N, B to the N. So the numbers of A and B's are the same, and also C to the N. Okay, that's a violation because our context-free grammar memory isn't that extensive to remember all 3 of these relations, right? And they're all related to each other. Okay, and that's one of the cases. The other case is that if we have something like A to the N and then C to the M, and then B to the N, and then D to, or G to the M, right? Because, okay, A's and B's are related, and then C's and G's are related, but we have an intersection over here. So either we have a 3 plus relation or some intersection, right? And this one over here, this one doesn't violate either one of these. It's just that A's is related to B's, where N has to be less than B's, right? So we could try and come up with the context-free grammar for that.
So
Um,
two variables can have the same power. Is that what you're saying?
yeah, yeah. So let's say we have uh A to the N and B to the N, right? What's the small, and let's come up with the grammar for that. What's the smallest thing we could come up with is when N is zero, right? If N is zero, then this whole thing would be empty. Or we have like, let's say N is one, then we would just have A, B. So it starts off with the A, ends with the B, and then we could recurse on that. So let's say we have A, B, B, then instead of choosing a lambda, it would choose this, right? It would choose, okay, A, and then I'm gonna choose A as B, and then I want to do it again. So S is going to replace, it's gonna get replaced by A S B again. So it's gonna choose A, uh, S, B, and then B, right? This S is getting replaced by this. And then in the end, S is gonna be like, okay, now I want to stop the recursion. I'm gonna choose a lambda. So it's gonna choose A, lambda, B. You don't really have to write lambda, right? Lambda is just uh something not the it's just the empty string. So this is just AAB. But you see, if you have two characters that is to the same power, the context-free grammar is a little bit strong to remember those. It could you could create a context-free grammar with that. So it's okay if two variables have is related, okay? It doesn't break that. What's the problem is three or more relationship. So like I say, A to the N, B to the N, and C to the N. Or you have an intersection. Intersection, right? So those are what it would break. Okay. Um, but our language is context free, right? Because it doesn't violate any of those three plus relationship or the intersection links. So it's valid. So we could try and come up with the grammar for it. So let me make these smaller, put it over here. And whenever it says a formal definition of context-free grammar, you have to write out the G's, the V's, and everything. Our grammar is it's a set of V and then S starting symbol. I mean, or you could just say sigma. Sigma is given to you. And then our production rule, and then our starting symbol, S. Right? Okay. And then our sigma is just I'm not gonna write it out. Again, it's just over there. And our production rule is what we're gonna create, and then our states is I'm gonna write out the states after I'm done creating the context-free grammar. So let's start. I have my S, right? The number of A is less than the number of B's. So let's say I have one more B than I have A's, right? Uh, this is going to represent my number of A's or my A's, and then I'm just gonna have a B right there, and then I'm gonna have B's after that, and these are all in alphabetical order, right? So it starts from A, B, A, B, and then C. I don't think Obrenic likes when you write like C because it looks too similar to the lowercase. So I'm gonna use a different variable. I'm gonna use D to represent my C's, and then A, B, C, D, E, okay, to represent my G's, right? Okay. So for my A's, it's going to be okay, less than the number of B's. What if I don't have any A's? That's less than B's. That's less than one B, right?
But
Nothing is.
wait,
I'm
Patron,
sorry.
why you give the single B after the capital A?
Because I'm saying like, okay, what if I have no A's? Then I'll still have a B, right? I'll still have a B, and then I don't really care about my I don't really care about the C's and the G's for now. So the single B means that okay, I have at least one B that's greater than the number of A's.
Oh, okay. Thank you.
Mm-hmm. Okay. So if my A's is nothing, then I still have one B, right? That's greater than that. Or if I have one A, then I could have a B after that, right? So for every A, there's a B, right? And then for every B, there's just any B's. Or I could have nothing. And then for any what was my DC? Okay. For any D's, I'll have four C's. So that's a C, 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 C. And I could recurse on that. Or I could have nothing. And for my G's, I could have three G's or nothing. G, 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 then okay, I'm done with the context-free grammar. Anybody have any questions?
Oh, yeah, Professor. Still for the B. I mean, if I just break down the Bn to the two part, one part is a B powered by n, and another part is a B powered by P, or another thing. Is that right? Because if the A is empty, is so we still have a B powered by P to satisfy the condition.
So I'm assuming you're talking about replacing this one B with the P and then make that
No
P
P,
go
no
to
P.
B.
It's a B power than P, right? I mean the
Okay,
B power by P.
B to the B power
The B power. And yeah, can I write like that?
for this.
Yeah. No, this is the we can break down the b power m, break down it to the b power n multiple the b power p.
I'm not sure if I understand your question. Are you talking about breaking down this power? M equals 1 plus P,
No, the n plus p.
M plus P. Okay, okay, you could do that. Yeah, you could do that.
And
Like that?
no, just it's like I can write like m equal to n plus p.
N plus
m
P.
m m
Oh,
m equal
okay.
m equal to no m equal to not plus equal
Equal
n n for Nancy.
N
Oh yeah, plus p.
plus P.
Yeah, can I write like this?
N plus M equals N plus P. You could
Yeah,
do that.
I can
Yeah,
do
yeah.
that. Okay, thank you.
Mm. Over here, I'm just making, just a single B greater than my A's. So like for example, over here, right? You see for every A I have a B. So I would have something like A, B, B, right? If I have if for A I choose nothing, then that means my A would be nothing, or else I choose this. So I choose A, B, and I replace this A with the sigma. I mean not a sigma, with the lambda, and I get A, B. And then if I put A, B over here, I still have this B, right? From over there. And then for my B, I could not choose anything, but my B's would still be greater than my A's, right? Or I could choose a single B and then continue on it. But my A's would be less than my B's. And then I would have, C, C. So I choose 2B to replace this uppercase B. And then I would have C, 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 and then G, G. Okay. Any questions? If not, we can move on to part B. And then on the 30-minute mark, or like 3:30-ish, we will switch gears to review for regular expressions and such. So part B, we want to draw the state automaton. Oh, shoot. Okay, paste it. It's the same one. Okay. Um, A to the N, B to the M, and then C to the 4W, and then G to the 3L, right? And now I want to draw a state automaton, draw a state transition graph of a finite automaton that accepts L. If such automaton doesn't exist, state that it doesn't exist and prove your claim. So, okay. So like I said, for context three, it's broken by three plus relations, right? So if you have A to the N, B to the N, and C to the N, uh, or if there's intersection. Okay. But for regular languages, it's a little bit different. So for regular languages, if this is for context free, right? context-free grammar or context-free languages. This is for context-free languages, and for regular languages, what is not regular is that if you have arbitrary dependencies. So let's say you have a to the n and anything else depends on a. So if you have the same number of a to the n and b to the n, this is not regular. It is context free, but it's not regular because you could never make a uh what do you call a regular expression on our automata that accepts that could track the number of A's and the number of B's, right? Because this is an arbitrary number. N is an arbitrary number. So if you have, let's say, 3A to the 3 and then B to the 3, that could be regular because you know that N is 3 and you would need 3 A's, right? A and then another A and then another A to reach the final state. This is another state, to reach the final state, right? But if it's arbitrary, you don't know the number. So, uh, this is not clean star because clean star is zero or more. If you have something like A to the star and B to the star, that's still not accurate. So there's no way to track it. If you have something like this, it's not regular. That's one of the cases. The other one is uh like similar, but like arithmetic constraints. Let's say you have, the number of A's is two times the number of B's. So you have A to the n and then B to the n. They're both dependent on each other, right? That's gonna break it. Um, so that's where pumping lemma comes in because we have to prove that it's not regular by contradiction. So the thing is that Obrenic will give you guys the template for the second midterm for pumping lemma, and the template uh will basically give you that it's gonna start off with something like, okay, let's assume the opposite. Let's assume that it is regular. I should have gotten the template for this. But the pumping lemma is gonna assume that okay, it is regular, right? Let's assume that L is regular. Then there's gonna stay there. Then we have to define a pumping constant, or it might be defined in the template that their K or something is a pumping constant. And our pumping constant is basically something that we define to make our window small enough so that when we pump up or down, it violates one of the properties, right? So K is our pumping constant. Don't worry about the value of K too much. We're just stating that it's our pumping constant by the pumping lemma. Then we're also going to find a word in L belonging to L. So over here, we could get rid of the C and the G, right? By setting W and L to 0. If we set them to 0, then the value of C's and G's would become 0, right? And we'd just be left with A to the N and B to the N. Uh, there exists. I'm gonna call this W0 because this is something that I just got it from the language, right? And when I pump it, I'm gonna call it W1. W0 equal A to the N and B to the um, M. And it belongs in the language because you just set it W and L to 0. Okay. So you'll be able to pump that. And we're gonna say that the value and we're gonna set this, right? The exponents. We're gonna set the exponents to be greater than our pumping constants, which is K. Say N plus M is greater than our pumping constants, which is K. And we're gonna say that the we're gonna decompose our pumping what do you call our pump I mean our word into X, Y, and Z because that's what it decomposed to. So uh the decomposition of W0. You could pick any three letters. I'm just gonna say X, Y, and Z. And Y is gonna be our pumping part, and the window is gonna be X and Y for regular languages, okay? Where Y is our pumping part. I might run out of space, so I'm gonna make this a bit smaller. So Y is our pumping part and our pumping window. Pumping window. We want to make the length of the pumping window at most K, right? So K pumping constant is gonna be what our pumping window could at most, fit. And pumping window X and Z is gonna be at most K. Right? And okay. We could say that our K, our length of the pumping part is not empty, right? Because if it is empty, then it wouldn't make sense. It would just be A to the A, it would just be what do you call? It would just be the empty string. So what we could say is that after pumping, we get we get X Y to the P P is how much we pumped, and then Z. Pumping just means that we, do it many more amount of time. So we get X, Y to the P and then Z. And when we when we say pumping up, we could now say that A to the N plus P and then B to the N. Sorry. I should set my WI to that. W1 equals this. Um, it is very wordy, but I'm pretty sure she's gonna give you guys the template for this. So you just have to come up with a W0, right? Or just a W that's belonging to L. And then also the pumping constant, you just have to say the pumping constant is going to be less than our exponents. We are doing that on purpose so that when when we pump up, we get something that is out of the window. We don't want to pump B2 at the same time because if we do that, then we might not, that's not how the pumping lemma would work to prove that we get something that's out of the language. Now this breaks this first property. You want to say that it breaks the first property where I mean actually it's the second property where the number of A's is less than the number of B's. And when we do that, you see that we actually end up with more A's than B's, and it breaks the second property. So by since W1 is not in L, you could say that by pumping lemma, L is not regular. All right. There's also other videos that is in the server, in the Obrenic server, so you could take a look at that. I think they explain it a bit better just because they also use the template. And yeah, that's basically all you really have to do. Just, specify some constraints and then the window. And the hardest part is just to, knowing when to use pumping lemma or knowing when something is regular or something is context free because these are like, a lot of constraints. Um, if this wasn't over here, the number of A's is less than the number of B's, then this would have been regular, right? Because the number of C's is divisible by 4, the number of G's is divisible by 4. Those you could write a context, I mean, those you could write a regular expression and also an automaton for. You just, this is the only thing that's really breaking it. All right. Any questions? Okay. Daniel, do you want to switch gears?
Yeah, sure. Can you hear me well?
I could hear you well.
Okay. Thank you, Roshan. Um,
All
so
right.
uh, we're planning to right now just go over the regex, um, context-free grammar, and then also the automatons. So we're going to go over some problems for that. Feel free to stay if you still need help with this. It's still a relevant concept in exam two as well. Okay. Let me see. Can you guys see my screen?
Yeah, I could see your screen.
Okay, great. All right. So, this is the problem we'll go over first. It says, let L be the language defined by the regular expression, and then we're given this one. Write a complete definition of a context-free grammar that generates L. And the way I like to start this is very simple. First, we're going to mark up the regular expression. And the way to mark it up is to just assign a variable name or like a group to all of the parentheses groups, parentheses with a star or just a star. So all of these we will give a variable name. So let me show you what I mean by that. Immediately I see over here, this whole group is a big parentheses star. You see the parentheses here and then a star. So I will give that a name in itself, and I'll call that A. And then I'll do the same over here. I see parentheses here. I'll call this B. This group I see star. I call this one D. Over here I see parentheses. I will call it E, right? Where else do I see parentheses or parentheses star or just star? I see over here, I'll call this F. And then here I see parentheses, so I will call this one not G, because G stands for the grammar. I'll call it H. Okay, so that's how I would mark up any regular expression before I start anything. So remember, parentheses with a star or just a star. Now we can begin writing our grammar. The grammar starts always with G equals V, sigma, P, and S. V is your set of variables. So that's all the ones we just labeled. So we can already write it down. S is one of them. S is the big string. The whole thing is S. Okay, so let's write down S and then all the ones we listed. So we have A, B, D, E, F, and H. So that's our variables. Sigma, this one is just your alphabet. And usually she will give it to you. And let's see if she gave it to us. She gave it to us right here. And so we just list the same stuff she already wrote. So what she has here, A, B, C, and G. And then P is the production set, meaning, we'll get to this, but it's basically what do our variables become? Define basically our variables, each one. And the production set is where we start defining our grammar. And we start with our starting string. We say, what is S? That's the very first one we define. What is S? Well, S is this whole thing. And what is this whole thing? The whole thing is, if you read it from left to right, it's this group here, and then this small group, and then F. So this group was A, and then what we didn't label, G, B, B, A, and then F. So it's just what concatenates to make group S, to make the whole string. What is put together? It's a concatenation of A next to G, B, B, A, next to F. Okay? And then we go on to define everything else. And we'll start with A. We'll just go in order. What is A, right? What is A? A is this. Remember, A is this one. And A is a concatenation of B next to this lowercase b, and then D, and then this whole E over here. Okay? So then, and by the way, A loops on itself because there's a star on A. There's a star on the whole group A. Whenever there's a star, we will repeat A twice, and then we write lambda, and then everything inside A. So what is A composed of? It's a concatenation of B, and then a lowercase b, and then D, and then E. So I'm literally just reading it left to right, the group A. I'll clean it up a little bit. But you see A is composed of, oh, I can't even, okay, oh, it's an eraser. A is composed of this group B, then the little b, then the D, and then the E. So just read it left to right and write it as it is. And the reason I did this A, or lambda is because of this star. Meaning A can become two A's, and then each of those two A's can become two more A's, and then etc. So we can keep basically adding A's, and that's what star essentially means. It means zero or more. And if we want to pick 0 times, we pick lambda. Okay, so that's how you would indicate that there's a star, a clean star. And then we move on. We define B. And we literally just do the same thing. What is B? B is this group here. And B is just saying it's BA or GCB. And the way we put or is just with this bar, BA or GCB. Then we keep going, we define D. D is this one here. And this one is just C star. Remember, when there's star, just repeat the variable, add a lambda, and then add whatever is the base case, whatever is inside. Inside is C. Okay? And then we keep going. We define E. E is composed of AA or CB or GG. And there's no star on E, so it's just those three terms. We list them and separate with the bar. Okay? So it's very simple. Once you've created your outline with the variables, it becomes very simple. F is likewise, it's just going to be AB concatenated to H concatenated to GA. So AB next to H next to GA. The reason I'm not putting a bars here is because bars mean this one, the OR. And we don't have OR. They're just right next to each other, you see? And so we don't put the bars. And by the way, on F, there's a star. So on F, we will also write this FF or lambda. Meaning I can repeat F 0 or more times, right? 0 or more times. And lastly, we have to define our last variable, H. H is just over here, A or C. So literally A bar C. And that's it. That's how you would do this context-free grammar and any context-free grammar conversion from a regular expression for that matter.
Excuse
Okay?
me.
Yeah.
So for H, I mean, not for H, for F, why did you
Mm-hmm.
change where the name of the function goes?
Oh, you mean like where I put this in the end?
Yeah. Why'd you put it at the end?
Okay, because this or thing is commutative. The bar is commutative, meaning we can switch around the places. Like for example, here I can just do GG or AA or CB.
Oh, it
I can
doesn't
switch
matter.
them. Yeah, doesn't matter.
Okay, all right, gotcha.
But if they are like this, like concatenated to each other,
Mm-hmm.
think
Then
about
usually
it
doesn't
like you're
matter.
putting
Okay.
two strings together. Let's say A, you're just putting it right next to B. So what will you get? You'll get AB. But if you switch it around, you say B and then A, you put them together, you get BA, which is not the same. So we can't switch concatenations together. Okay?
All right.
So that's this problem. And then we'll go on to do a automaton for this. Let me see. So for automaton, it's a little different. Let me rewrite this down here. And these topics probably will occur on your second exam, for sure at least once, maybe twice, even 3 times. So you do need to know everything from exam 1. Okay, so to create an automaton, we're doing something a little different, where we just read it from left to right in the same groups, and we basically assign states and go to the accept. Okay, similar to what Roshan showed, but Roshan did it for Turing machines. Here we're doing it for regular expressions. Yeah. And so we start off in our starting state. I'm reading from left to right. Okay. And immediately I can see this group here, BA or GCB. Okay. B and then A or GCB, they will get us both to this point, right after or right before the B. They will both get us right before the B. So right before the B is where I will have my next state. Okay, and they both get us there. So G followed by C followed by B. They will both get us to the same place. Okay. And then after this, we take our B, which is this one, and that goes to another state. Now, C star means we can repeat C as many times as we want or no times. And when we have a star, usually we will loop around the same state. Okay? We will loop around, and there's another way to do the Kleene star, which I will show in a bit, but this is the easiest way. And so once I take B, you can see I can do C as many times as I want, right? I can pick C as many times, or I can just move on. That means 0 or more. That's how we signify that in the automatons. After C, we have this group here, which says AA or CB or GG will get you to the same state. So take either of those 3 paths. So here, first path is A, followed by A. Second path will be C, followed by B. The third path will be G, followed by G, and they will all bring us to the same state. Okay, which is this basically the state where we are after we do this group here. Okay, and then finally I see a star, and this star is on everything we wrote so far. Do you see that? It's on everything. And so that means that we have to loop back, and this is the other way I was showing you about the Kleene star. We go back, and also we can go forward with lambda transition. Basically, it means we can go all the way back and repeat this. So we go literally, when we reach the end, we go all the way back to the beginning and we repeat it. Or when we are in the beginning, we can just skip all of it without doing anything, which was what star means. Star means 0 or more times. So we can just pick to do it nothing, no times. Okay. So that's how we can also do a Kleene star. And then after this, remember we are over here. We're over here and we have GBBA. So G followed by B, followed by B, and then an A. Okay, and that gets us to this state over here pretty much, right after the GBBA. That's where we are right now. And then lastly, we have this sort of group here that we could also write down. So literally A, and then B, okay? And then what do we have after that? we have A or C. So A or C will get us to the same state. And then G followed by A. G followed by A, and we can loop all of this. So that means I can go all the way back to where I was. G followed by A. And so the reason I went back is, remember, when you loop, you can either go back or you can do the two lambda transitions. So I can equally just do this. Go A over here, and then I can do like this, lambda and lambda back. This is also okay. This is fine. And the accept state is over here. Okay? So both approaches are okay. You can use both, you can use one or the other, whichever one you prefer. Okay, so that's how you would do this problem. Any questions? This one's a little harder than the grammar, in my opinion. Any questions on this one?
What would it look like if we had an automaton that did not exist? Like we couldn't make one.
You mean like if it's not regular?
Yeah, I'm like, yeah, so it's asking us if such an automaton does not exist. Yeah, like what would that look like?
Oh, then if you determine that the automaton doesn't exist, then you would just do the pumping lemma proof, right?
Oh,
What
okay.
Roshan showed. And I think that's the hardest part, like knowing when it does exist, when it doesn't. Because let's say I did all this, right? And turns out that whatever I was doing actually doesn't exist. And then I just wasted all my time and I'm getting no points for this. So you see, we could have just wasted like 10, 20 minutes. Okay, maybe a little less, but we could have wasted time drawing this whole thing when it actually didn't exist. Okay? In this case, it did exist, but you got to know when it doesn't and when to actually go about the pumping lemma proof. Okay? All right. This problem will probably always show problem 2. It always shows just by looking at the past exams, pretty much in every past exam, you will get either a CFG or this one, context, or I'm sorry, a CFG, or we can get the automaton, which is what we got over here, or they will give us a regular expression like this one here. And then they will ask us to convert to the other two. In this exam, she gave them 2 questions on it. So it's pretty much 3 points if you know how to do it. And here we're just going to do the exact same, but converting from the automaton to the other 2. Okay. So for part A, it wants us to convert from the automaton to regular expression. And so the first thing, I would obviously start with the start state, which is the state with the arrow next to it, and then see what it's doing. So it's taking A and it's taking B, and they're taking both to different paths, right? So let's trace one path down, and we write down what's happening. Always trace one path at a time. Let's trace the top one. So A first, so just literally write it, A, followed by C comma G. Okay, if you have something like this, C comma G, right? It's the same as saying C or G lead to the same other state, same next state. So it's the same thing as writing that. Otherwise, can be written as as C union G in our regular expression. And then let's move on. Then we have a B. So just write the B. I'm over here. And then we're doing C to some arbitrary state, and then A or G will get us back to where we were. So what does that mean? That means a loop or a clean star, where we have C or C followed by A or G. C followed by A or G. So C followed by A or G as 0 or more times, as many times as we wish, right? So once we do this, we go back right after the B, which is over here. Okay, and then B or G after that. So B union G, and then C or G loops. So C union G star. There's a loop on itself, it's a star, remember. And then lambda to the end state. A lambda transition, like we said, can just be taken without any character. So basically lambda over here, and lambda means just a blank space, so really nothing. So this is our first route. We're done over here. Our second route, and you can see it splits. If it splits, it's an OR, okay? Or we trace this path now, and I'll write it in red. We start off with B, and then look over here. We have these lambdas. The lambdas, in my head, I'm already thinking, okay, there's a Kleene star. So I will start with parentheses and a Kleene star. We don't know where, but we will start tracing it and we will see. So first we take a C, okay? And then we have two paths. Starts off with B or G, and then C star. So C as many times, because C loops on itself, and then A, and then A. Okay, that's the first route we can take. The second one here is C followed by C or G. So C followed by C or G, and then a B. So after we take either this one here, which is the top, or the bottom, okay, then we finish off with a B. Okay. And there should be a parenthesis here to separate this. Okay. So C and then whatever over here, the middle part, and then followed by B. All right. And then lastly, A or B will take us to our accept state. So A or B, this one. And so that is how you would do conversion to regex. It's a little more complicated, but if you just know how to trace it, I think it's pretty straightforward. Straightforward process. It doesn't really require much thinking. All right, and then context-free grammar. If you notice, once we have the regular expression, right, making the grammar is pretty straightforward because we already did it in the first problem. Okay, we label it first, and then we do the grammar. And labeling is just, remember, labeling is parentheses get a variable, parentheses star get a variable, and star gets a variable. Okay, so just to do the labeling part, I'll give this one a name. You can think of this or here, it separates these two over here. So I'll put parentheses, I'll give them variable names, just to format my string a little better. So I'll say this whole thing is A. And then this one I'll say B. Okay. And then I'll say over here, this is C. Or no, we can't use C. Let's say D. This parenthesis star is E. This inside here is F. This I'll call H. This is J. And then we keep going here. Say this one here, parentheses, the whole thing. That will be K. This one here, oh, we will leave it for now. We'll start the grammar for now, and then we'll keep going with the second part. But for now, we can write down what we know. We can write G equals V sigma P and S. V we'll leave for now. We'll just say S because we haven't assigned all our variables yet. We're going to do that a little later. Sigma is just the alphabet. She doesn't give it here, it looks like, but we can kind of see what we're using. We're using A, B, C, G. I really don't see any other letters. So I'll just write A, B, C, and G. And then our production set. S is the whole thing. The whole thing is this whole A union this whole B. So A union B, right? That means A bar B means A or B. Pick one path, right? And then once we do that, we start defining what A is and then what B is. So what is A? A is going to be this little A, followed by D, followed by the little B, and then E, H, and then J. So a bunch of things. Okay. A, D, B, E, H, J. And then we start defining one by one. What is D? D is, well, it's just C or G, which means C bar G. And then define E. What is E? E is a little more complicated. I can see E is C and then F. And it loops on itself. There's a star on it, on E. So we say EE or lambda and then CF. That's our whatever's inside. CF. And then, well, what is F? F is just A union G, which is just A bar G. Okay? And then we keep going. I have H and J left to define. H is just B or G. J loops on itself. So J loops on itself. So it's just JJ or lambda or whatever's inside. C or G. All right. And then we keep going. We're done with A. Now let's define B. We really didn't define B yet. So B, B looks like it's a lowercase b. And then let me clean this a little. And then K, right? And then K, which is this whole thing here. And then this here, which we didn't define, I'll call it M. Okay. So B, K, and then M. And then what's K? K is this whole thing. it's gonna be, well, first of all, it loops, so it's kk or lambda, and then lowercase c, and then the little group L, which is this whole group here, and then lowercase b, so C, L, B. Okay. And then what is L? And just define L. Let me clean it a little. Too much going on. We defined L as this group here. This one here, L. So it was the B or G followed by C star, A, or C union G. Okay. So I'll call B union G, or I already have a B union G group. So this is just the same as H. This group here is the same as H. So I'll say H, and then C star. C star, I'll give it a variable name. I'll say N, capital N. So H followed by N, followed by A, right? This lowercase a. And then we have we have a union. So that's a bar. A lowercase c, followed by C or G, which we already have defined. That's D. I won't redefine another variable. We can just reuse it. All right, so that's L. Let's keep going here. We haven't defined N, so let's define it now. N is just C star, meaning N or lambda or C, the base case, C. And then lastly, what haven't we defined? Let me see. I believe M we haven't defined, which is the last part here. M is over here, A union B, which is just A bar B. And then I believe we are done. Yeah, we should be done here. And then, oh yeah, don't forget at the end to populate your variables list. So literally just read from top to bottom all the variables. So S, A, D, E, F, H, J, B, K, L, M, and N. L, M, N. And that's it. That's how you would do these problems. Did a little quickly because we were a little short on time. But these problems are definitely going to show up on the test. And I think if you can do them quickly, it's definitely easy points compared to something more convoluted like pumping lemma or Turing machines, which will still give you points, but it's going to be definitely harder to get and less sort of brute force than these problems we just did. All right. Any questions on this?
All right. Thank you guys. Thank you, Daniel, for going over that.
Mm-hmm.
I had a comment. So if you guys have it, please fill out the feedback form that I'm gonna post
Mm-hmm.
in the chat. Thank you.
Yeah, guys, please. The feedback forms, basically, they give us the ability to get more funding and be able to host more review sessions like these in the future. So you can please take a minute to fill those out. And if you have any questions, please let us know about anything we covered today.
Thank you.
No problem.